Okay, guys. So today, well, in this video, we're gonna do properties of groups, basic properties of groups. So the good thing of this is we're gonna do some proofs, and these are good for any groups. So are good for permutation groups, for cyclic groups, and many groups we're gonna introduce very soon. Um, so, and they are just based on the three properties of groups that we have, or three and four groups, four properties of groups, right? So remember last time we give several examples of groups, and these were my properties of groups, right? So for a group, you need a set, you need an operation, define an operation on the set. To define an operation on the set, you need to define it on the G cross G, right? The same for real numbers. If you have multiplication for real numbers, same thing, right? So you have 5 and 3, you define 5 times 3. It's just notation, right? That's 15. Just notation. So what is important is that the operation you define stays in the group. Okay. So for example, I could define an operation that is not on the rational numbers. For example, I could do rationals, and okay, but this is in my other computer, not this one. So rationals over the rationals, and then you got, for example, Q and R, and you define it. Let's say you want to define it like a square root of 2 times Q times R. So this is not a good definition because square root of 2 is not on the rational numbers, right? This is not a right operation. This will be an operation over the real numbers. But still we need to see if that will make a group or not, whatever. I mean, it's not gonna make a group because it's not lines on there all day. But so this might be silly, but those kind of mistakes we do, So this is not an operation. Okay. So this operation you define, it has to be associative. It has to have a identity element, and it has every element of the group must have an inverse. Okay. And that's pretty much those three properties that we need. We're gonna define, we're gonna do some basic properties of groups. Well, soon we're gonna do symmetry. I think people are gonna like that because it's related to the Rubik cube. I don't have a Rubik cube around here. Okay, so first proposition. So the identity element in a group G is unique. In a group G is unique. So that is, there exists only one element E in G such that EG equal GE equal G for all G in G. Okay? So this is the proof. So I made my proof before. So so let's see be another unit element. Okay. No, identity element, no unit. Identity. Identity. Oh, I think I'm going to do that. My razor doesn't. Identity element. Okay. So the idea is to play with these properties. Okay. So I will invite you to stop the video and try to prove it yourself. So my hint is let C be another identity, and at the end you're going to have to prove that C equals E. Okay. So that's what I'm going to do. So try to play with those properties over here and try to prove it. Okay, so I'm gonna do it. So since C is another identity element, CG equals GC equals G for all G in G. You also try, you probably also try contradiction. That's good too. You know, I did it like that, and it turns out that the book did it the same way. Sometimes the arguments a little bit different. I stay with mine if I'm not making a mistake. It's just give you my proof. So, and then we also have E, right? So what I did was, okay, so since E is the identity, we have E equals C times E, right? But C times E for E being the identity is equals C, right? So it's like this. This one, C times E equals E because C is identity. And this one over here, C times E equals C because E is the identity. Either way, E equals C as we wanted. We can say therefore E equals C. So when I was doing the PhD, I took 4 astral algebra classes. So 2 at the master level and then 2 at the PhD level. And there was 1 qualifier, so these qualifiers. And then for the part of group and rings, we had to solve like 17 problems in 2 hours. I remember I solved 13. But yeah, you had to, so this, you had to solve a lot of problems, but they are you kind of get used to these kind of arguments. Okay. So yeah, it might look weird. It's your first time, but this kind of argument is showing all the time. So it took me 2 minutes to put this one. The next one, it took me like maybe 4 minutes to fix. Okay. So proposition. This is a proposition. Let's call it proposition 2. But the best thing you can do is try to do it yourself. And then when you will, because you try to put it together, and then when you see it, you said, oh, that's what it's supposed to do, and then that's what you learn. So if G is any oh, what is happening? Element in a group G, then the inverse of G denoted by G inverse is unique. So if G is any element in a group G, then the inverse of G denoted by G inverse is unique. Okay, so this one gives me a little bit more work. So also please try it, try to prove. And what I come up with, so I did several tries, and then this is what I come out with. Okay, so let K be also the inverse, or an inverse, let's say, an inverse of G, right? So you need to put together, like, at the end, you need to get K equals G inverse, okay? Because that's what you want. So they don't necessarily have to be the same, because in the proposition, in the statement, in the definition of groups, it doesn't say that G has to be unique. But so you assume there is another inverse for G, and then look at this. We're going to see the properties of groups. So I'm going to do it like this. So G, this is what I want, right? K equals G inverse. So I'm going to look at how I'm going to force it. I'm going to do G inverse, G, K, right? Let me see that. Oh, okay. So then, so I had to. But that's, let me put it like this. So I'm gonna write it like books do, but the process of thinking is not like this. So that sometimes I feel like teaching you the wrong way, because this is not how you come out with the proof. Now, I'm gonna try to do a proof in front of you like this, like live, right? Without any preparation. But now look at this is how the book will do it. So look at this. So G inverse equals to G inverse, correct? But then we're gonna do the identity, G inverse times the identity on this side, and then G inverse times the identity on this side. So in both cases, I get G inverse, right? So this, I haven't done anything weird. Now, I'm gonna change E by JK, right? Because let K be also an inverse of G. That means GK equals KG equals E. So then you have here E. I'm gonna put KG. Okay. So you notice I'm using the properties, right? This is my definition: GK KG equals E. So that's my, if it's the inverse, if K is the inverse, that's gonna be true, right? So I need to force, I'm gonna implement it, that statement in my proof. And now I use by, so let's put then the following is true. By properties of groups, we can rewrite this by associativity, right? By associativity, and we can do G inverse G K equals, I don't know, hold on. I want to do GK. I'm gonna leave this one like this. KG G inverse. So I can rewrite this one like this one, right? Associativity of groups. And what is this? This is the identity. KG inverse is the identity. Okay. KG is the identity because of my assumption. Therefore, K equals J inverse. Therefore, the inverse of G is unique. Okay? That's how the proof goes. So we have proof the identity element is unique and the inverse of any element is unique. So let's see, let's do one of the book, another of the book. Oh, this I already did this one though. Let's do it. I did it for matrices. Probably you wonder where did he that come? Why did he came that from? With? Oh, how he come out with that idea? Well, it's probably because I had done it before, right? So this is, in general, this is true for groups. Proposition. Let G be a group for any G in G. Oh no, sorry, no, doing another one. Let G be a group multiplication. Let's see. Multiplication doesn't work. Cannot make mistakes. So let's see. Can I replace with this one? Well, anyway, I'm gonna have to let G be any group if A and B belongs to G, then AB inverse equals B inverse times A inverse. Let G be a group if AB is then. Yeah, so that means this is important. So all those propositions are important because there are things we know from the real numbers, from the integers, but we never had wondered if there is another inverse for 1/3. Okay. And by the way, I didn't say it before, but when we were talking about classes, remember I talked about, I don't want to write here because then, so C3, right? So C3 we said is the class 0, 1, and 2, right? Turns out that the rational numbers, they are classes. We never had been really said explicitly. But when you have 1/2, 1, 3/4, and so on, right? But turns out the 1/2 is the same that 2/4, the same that 4/8, and so on. This is a class. So this is very interesting. We have been using classes all the time, and we haven't really been aware of it. Okay, so 1/2 is really a class. So anyway, so what I'm saying this is just because all these properties that we're talking about are in the sets we have been using, and we just give it for granted. Okay, so we need to prove this. Okay, so by previous proposition, we know that the unit is unique. So I just need to prove we need to prove the three properties, right? So in general, let's put it like this: K is an inverse of G if Kg equals Gk equals the identity. Okay, so that's what we need to do. So we need to prove that AB times B inverse times A inverse equals then we need to change the order. Well, let's put it here. B inverse A inverse AB, and they're both the identity. Okay, that's what we need to prove. But you see, this proof is easy because by properties of groups, associativity, this is equals to by associativity of the operation of groups. that I'm not putting all the time because I don't want to do circles all the time, right? But it's there, right? So I don't want to do circles all the time, so I'm omitting it. So it's A, B, B inverse, A inverse, passed by associativity, right? But this is the identity, so I got A, E, A inverse. And by associativity, you can do it like this. So you go A inverse, sorry, identity times A inverse is A inverse. So this is identity. Similar here. So this gives me the identity. Now this one is B inverse A inverse AB by associativity, right? So now this is the identity. So by associativity, I can do it like this, right? So that's B inverse B, and this is just E. So this guy is equals to the identity, and this guy is equals to the identity. Therefore, these two guys are the same. So, I mean, I'm saying, sorry, yeah, the whole thing. Oh, this thing over here is the same as this thing. So we have proof. AB times B inverse A inverse equals identity, and similarly B inverse A inverse AB equals identity as we wanted. So pay attention to this. B inverse A inverse equals AB inverse. This is just notation, okay? AB inverse is just notation. We don't know what is that, right? So, but they are telling us is B inverse times A inverse. So this proposition is giving us the explicit inverse, okay, of the multiplication. So it's just like a matrix. You know, let's say I said 3, 4, 5, 6. Let's put it like this, 7, 8, 9, 10, 11. I can find the inverse of the matrix. What is it? Well, we need to do all the math, right? As we have learned in linear algebra. But this is just notation. We don't know it. So when I put it like this is just notation. But it's saying here, this is for a product. So that's if I had the product, like this one times 6, 5, 3, 2, 1, 6, 8, 9, 10. The inverse of this whole thing is gonna be, this is A, this is B, is gonna be B inverse, A inverse, if they exist, because it could be that these guys don't have inverse. Okay, so I have to check the terminal and all that. Okay. Okay, so another one. So let me do this live too. So the problem, sometimes live is not convenient because since I'm processing, maybe the proof is not written the best way. You know, so I don't know if you guys prefer me to try to do the proof right in front of you so you see how difficult how is the process of thinking, or just want me to give you the proof like a book, like. But again, I'm not sure. It's like I try to do both because and just when you read the book, it's like everything is revealed. So you just are reading. You're not paying attention. You're not trying to think by yourself. Okay. So here's if I'm making a mistake, you're thinking, oh, but why did he didn't do this? Why did he didn't do that? So you somehow you are trying to help me. So I think that's useful to keep you active. So proposition. So try to help me. They say, oh, why did he didn't do it this way? So let G be a group. Sometimes people email me and I said, oh, you try to do that, and they do. So uh, Emily, maybe Amelia, I don't know how to pronounce her name. She had sent me several homework that I said, try this pronoun, and she does it and send it to me. So I appreciate that. I appreciate that a lot. So let G be a group for any A inverse equals A. Let G be a group for any the inverse of the inverse is A. Okay, so I'm gonna let's see. I haven't done. And I'm sure I did it a long time ago. What? 14 years ago, maybe. Way more. Like 16, 17 years ago. Let's see how my long memory. But it's not memory, it's logic, right? So let G be a group for like point, right? Dot. For any, the inverse of the inverse is A. So again, this is just notation. So what I'm saying, so let K, that's the way I'll do it. Let K be the inverse of A inverse. Okay. So I'm gonna prove that K is A, right? So what I'll do, so by properties of inverse, this is true, right? So A inverse times K equals K times A inverse equals the identity. Oh, no, but I want the inverse. This kind of looks like not trivial, no? Is that all these problems have the same thing, that they look trivial. So let's see. Let K be the inverse of A inverse. Therefore, A inverse K equals K times A inverse equals A. So what I want is K equals A. Okay, see, this is what I want, okay? So, oh yeah. So what I will do probably will be multiply everything to the left times A. So let's see what happens. So if I do that, I'll get A times A inverse times K equals times A times K times A inverse. But then I've got A times E equals A. And then all this comes, this is E, K, and then there will be A times E equals A. So this is K and this is A. So conclusion, I don't need this middle guy. Okay? Because, okay, let's read the proof. So let K be the inverse of A inverse. Therefore, A inverse K equals E. That's the definition, right? So let's say, I guess multiplying, maybe there is a better term for that. Multiplying times A by the left on both sides So I got A times A inverse times A and A E plus E. Now, by associativity, right? So I do these two first. So yeah, so you see, this is where we have to be careful. Yeah, let me do it like this, because I multiply A both sides, right? So here these two have parentheses, and this one doesn't need parentheses. By associativity, right? I can do A inverse K equals A E equals E. So by associativity, I accumulate these two together. But this is the identity. So this is E, K, and we get K equals E. Therefore, A equals A inverse, as we want. Okay. So again, not sure this is more pedagogical or more confusing, but that's how it works, right? I mean, sorry, I'm trying to. I have to take this to fix because I cannot erase. Okay, no, sorry, I had to make it like this because. Let me see. Let me stop it and erase this, so it doesn't look that bad. Okay, so no, I couldn't erase it. So okay, so um, let me state our propositions and and please practice them. Okay, those are good exercises. Maybe they're good candidates for the exam. Okay. Um, I don't want to do everything either from the book. You guys can also try to do it um, yourself, right? So let's do this one. Proposition. So it is 1, 2, 3, 4. This is the fifth proposition. Let G be a group and A and B be any two elements in G. Then the equation AX equals B and XA equals B have unique solutions in G. Okay. Mm-hmm. So I want to do this. I'll let you do it. Okay. So proposition 5, proposition 6. All these are fun. They're not long proofs. So they're proofs of 3, 4 lines. So that's what those are fun. Those theorems like Boreal theorem and even the division algorithm proof. Those are long proofs. So those are not fun really. But these are fun. So let's do if G is a group, and A, B, C belongs to G, then BA equal CA implies B equals C and AB equals AC implies B equals C, right? Mm, yeah, I think that one is pretty easy, right? So you just need to multiply this guy times A inverse by the right, and this one you multiply times inverse for the left. Okay. This, you guys can do it. Yeah.